Okay, going over the answers here. The first one, everybody answered really quickly, so that's why I assumed that you guys did well, but I don't know, and we'll find out when we grade them. The first one, we have these 4 different types of molecular interactions. And believe it or not, 3 people asked the same question on the potential test questions. So this one had to be here, and that is, which of these molecular interactions is the strongest attraction? And so I did not list them in order of strength, so it wasn't A. Which one, let's just go with which one is the strongest and work our way down. Which one of these is the strongest is the correct answer. Ion dipole. Because with the ion dipole, you have something that already has a charge and something that already has a charge separation. Why is ion-ion not on the list? Those would have actually formed a bond making a molecule. So these are ones between molecules, and so the ion dipole was the strongest. The next after that, which one is the next strongest? Dipole-dipole, because those already exist. They just have to orient and then they bond. Which is next weaker? Okay, we see somebody's totally onto this. Ashton has studied. Good job. Dipole-induced, because once again, the dipole already exists, and so it just has to get close to something that's nonpolar and it can induce a dipole. The weakest one there is the induced dipole, because you have 2 things that basically shouldn't interact, but they have negative exteriors, so when they get close, those negative exteriors will induce a polarity that then gives them a mild attraction. And as we'll see at the very end of today's lecture, that's the key to how detergent gets your clothes clean, is that weak induced dipole bond. Okay, second question, which was very similar to the first. Which molecular interaction occurs between water molecules? So now we can immediately rule out 2 of them. Which can we rule out immediately? We can immediately rule out ion dipole and not induced, but dipole induced. The reason we can immediately rule those 2 out is because the water molecules are identical. So you're going to have the same type of thing for both molecules. So I ruled out the ones that aren't the same type of thing. And so then we just have to say, is water a dipole? Yes or no? Yes, it is. So it must be dipole. Next one, based on the rules we have learned, what is the correct and unique? I wanted to make sure you remembered that if there's more than one way to combine hydrogen and oxygen, you have to have the prefixes to tell you about it. So which is the correct and the unique form for water, which is H2O? All of them have hydrogen and oxygen in some fashion, right? Is it possible to have, well, first of all, the order. Which should come first, hydrogen or oxygen? Hydrogen. So we can rule out this one because it's in the wrong order. It's not the only thing wrong with that one, but it's in the wrong order. So all the rest are hydrogen and oxygen in order, but hydrogen and oxygen has multiple ways it can be put together. We've learned of 2 carefully. That is, when I talked about this, we talked about H2O2 and H2O, but there's also the ion OH minus, called hydroxide, actually. That's its common name. And so we can have different numbers of oxygen and different numbers of hydrogen. So we're going to need prefixes for each one. What's the prefix for 2, since hydrogen is first? Di. So it's going to have to be dihydrogen. And then what's the prefix for 1? Mono. So it's got to be dihydrogen mono. And then there is, I didn't give you every possible option. It has to end with "ide." So it's dihydrogen monoxide. So that would be the correct and unique formula name for water. And nobody goes around saying, I'm going to drink me some dihydrogen monoxide, because that would be goofy. Now the last one, and probably the trickiest one. What difference in electronegativity results in polar covalent bonds between atoms? So remember, we had ionic bonds is when one atom takes the electron from the other atom, and then you have two ions that are bound together by ionic forces, by opposite charges attract. What electronegativity difference is necessary to actually pluck the electron off? I didn't give you any bad answers here. It's going to be one of those three ranges. To take it off is going to take the most difference in electronegativity. Remember, electronegativity is how much it wants the electron. So the biggest difference in electronegativities is what's going to cause it to form an ionic bond. So this one here that had greater than 2 is the biggest option. That's going to form ionic bonds. Of course, which one would be nonpolar? That would be the one that has the smallest difference. And so less than 0.5 is nonpolar. And the thing that made this one difficult is the polar covalent, you have to remember, is the one that's in between. And so the correct answer here is between 0.5 and 1.6. And then you look at that and remember, there's a gap there, 1.6 for one and 2 for the next. What's going on in between? Well, it's really unclear. Could go one way, could go the other. So that's why they don't come to the same level. Okay, any questions about the quiz? Excellent. Let's talk more chemistry. I believe we're in chapter 16. Hope so. We're going to talk now about mixtures of things. We've talked about chemical bonds. We've talked about molecular interactions. Now we're going to talk about basically what do we interact with on a daily basis. So we're going to talk about mixtures and how those work. So first, actually a lot of this is definitions today. A mixture and a pure substance. Pure substance have only one type of element or compound. What's the difference in a compound and an element?
Element is made of one type of atom.
Element is one type of atom. A compound is more than one type of atom. So water, H2O, that's two types of atoms. So that's a compound. It's a chemical compound. But a pure substance can be either one element or it could be one compound. So water is a pure substance. Gold is a pure substance. A mixture has two or more pure substances. So if I have a mixture of gold and water, which if you were one of the children of Israel and you had been bowing down, worshiping the golden calf, you would have been forced to drink that mixture, then that's what we call a mixture in chemistry. So almost everything we interact with is going to be a mixture. If you want to get technical, the water you're drinking is a mixture because you know what it's not? It's not pure water. If it was pure water, it would actually taste kind of flat, I'm told. I've never gone and drunk pure water. And so we have impurities in there, minerals and whatnot, that make the water taste a little different than what we think is good. But here's an example. Sugar, ideally, is a pure substance. It's only one type of molecule. And so this is saying, let's suppose that your sugar is pure sucrose. There's more than one kind of sugar, right? Sucrose, fructose, there's different types. But say your sugar is pure sucrose, then it's a pure substance. but you put that sugar in your caffrey coffee, and now you're going to have a mixture because you have water and you have the sucrose, and then you have the other things that are in your caffrey coffee, which, you know, only chemists know. So that's a mixture. Simple enough? Gets more difficult. We have heterogeneous or heterogeneous mixtures, which are mixtures where you can see that there are two different types of things or more than two different types of things. And then you have homogeneous or homogeneous mixtures where it's so thoroughly mixed that it appears to be all one thing, even though it's not. So can you think of any examples of a heterogeneous mixture? My next slide has some pictures of heterogeneous and homogeneous mixtures. Can you think of an example of a heterogeneous mixture? Okay, a lemon. You can see it has the cell membranes and it has the juice and stuff. I was actually going to go even more. Well, I like food. That was food. I was going to go with trail mix. You've got nuts, which are excellent. You have M&Ms, which are excellent. You have raisins, which are full of insect parts. I kind of like raisins, except for that insect part. So that's a good idea. You know, yours was just as good as mine. So here's the textbook's classification stuff, and there's the pictures. Let's go to the pictures and then go back to that. The one I like from the textbook is pizza. Is pizza heterogeneous or homogeneous? It's very clearly heterogeneous. You can see that that has, you know, olives, which apparently some people love. I don't. It has some tomato, which I hope we can all agree is good on there. Has some basil leaves, has a tiny amount of cheese. I guess being vegan now, that's getting closer to what I can eat. But clearly you can see that they're separate things. It's heterogeneous. The snow globe. You have the water in there. You have the little flaky things. You can see that it's not the same. And granite. That's a piece of granite. The granite has a bunch of different crystals. Whoops, that's the wrong tool. You can see that there's a crystal here that's black. And then there's this here that's, you know, broad white areas. There's different crystals in it. So you can see that they're different minerals. We'll learn more about that later. Homogeneous. That's the part here that's homogeneous, the air. Our air contains about 21% oxygen molecules, O2, and about 79% nitrogen molecules, N2, and just trace amounts of other things. But you can't take the air and say, oh yes, I can see the oxygen here and the nitrogen here because it's so thoroughly mixed. You don't have to worry about, I breathed a pocket with no oxygen and I'm going to suffocate, because it's thoroughly mixed. And water, again, looking at the water here, not looking at the seafloor, it's a homogeneous mixture. And this here, this is a white gold wedding band. What is white gold? What color is gold? Gold is gold color. It's got a yellow color to it. Obviously, it's not yellow, so I'm happy with her saying gold. That's obviously a correct answer. This looks more like silver. How do you make gold that looks like silver? Well, it's not going to be pure gold. It's going to be what we call an alloy, where you have different types of metal atoms mixed together. And those different types of metal atoms give it its unique characteristics. You can't look at this and say, oh, here's a piece of gold and here's a piece of silver and here's a piece of, you know, carbon, because it's all so thoroughly mixed. So this is homogeneous, whereas this here, which is also different minerals, is heterogeneous. Okay, so now back to this classification. This is just breaking things down to make it easy for us. We have pure substances and impure or mixtures. The pure substances could be an element, one type of atom, or a compound, multiple types of atoms, but bonded together into one molecule, and they're all that molecule. So notice that's the same thing, that's the same thing, and that's the same thing. So there's 3 examples there in the compounds, just like there's 3 examples in the elements. If you had salt and carbon dioxide and ammonia, that would not be a pure substance. Then on the impure side, for our mixtures, we have homogeneous or heterogeneous mixtures. Heterogeneous, you can tell there's a difference. So, sand and water. If we looked at the ocean floor, we see the water, we see the sand, we say there's a mixture, and I can tell the difference. On the homogeneous, things that you can't tell, notice it gets even more complicated, words we haven't used yet. A solution versus a suspension. A solution is when the two are mixed together and we can't tell them apart. They're just completely mixed together. A suspension, they didn't actually mix, but they're so close together and evenly distributed that we can't really tell. So if you look at, for instance, milk is water with little fat globules suspended in the water. But when you look at the milk, you don't see, there's some fat and there's some water, because it's all thoroughly mixed. So it's a suspension because the water globules are separate from the water molecules, and one is just mixed in with the other. I don't have in this class nice pictures of that for my physics class. I actually have a picture under a microscope of water, or not water, but of milk, so you can see what it looks like. So the last 2 words here, solution and suspension, those were on that chart. The solution, all components are in the same phase. Suspension, you have different components in different phases. You have the little fat globules. Those aren't a liquid phase. You have in water, that's a liquid phase. So that's a way to see the suspension difference. You guys, except for Sam, you probably all know my beloved wife, right? What is the one thing that she believes will cure anything that ails you? It's not vegetables. Wow, you guys need to talk to Amy more. Come and say, I think I'm getting a sore throat, or I'm getting pink eye. I have hepatitis. Colloidal silver. Colloidal silver. Colloidal silver is a colloidal suspension where you have little small particles of silver metal that are suspended in water. So it's another example of a suspension. I can't believe you don't know that about my wife. After our first date, I had to go home and read up on what in the world is not a colloidal suspension, but colloidal silver. All right, our first question, which it's going to be open for polling, I'm telling you. Now it's open for polling. Yay. Is air, the air in your house, a homogeneous or a heterogeneous mixture? Okay. There's the answers we had. 5 people said it's homogeneous because it is mixed very well. 1 said it's heterogeneous because of the dust particles it contains. Nobody said homogeneous because it's all the same temperature. Very glad no one said that. And one person said heterogeneous because it consists of different types of molecules. So, in our house, we do have different types of molecules, right? And so that's going to make it not a pure substance, but a mixture. So this one here was incorrect because the person was confusing. It's a mixture because it consists of different types of molecules. And the differentiation we're looking for is if you can tell that they're different kinds of molecules or not. And 5 of the remaining people said, it's mixed very well. I can't tell them apart. At least at first glance, that's the group I would have fallen into. But the other person's not wrong. Because if you look at that air molecule through sunlight, you'll see there's this dust things floating through the air. And so it's also perfectly acceptable, at least in my opinion, to say heterogeneous because of the dust particles it contains. Those are not, nicely mixed. That's kind of like seeing the olives on your pizza. So, this is a question that I wouldn't ask this way on a test because you can defend either answers A or B. I ask it here in class because I want you to think about what the difference is and to be able to analyze these. Now to solutions. There's chemistry jokes that you might imagine about solution here. A solution is a mixture consisting of ions or molecules. Molecules meaning neutral, ions meaning with a charge. And you have the major component is the solution, it's the solvent, and the minor compound is the solute. So you mix 2 things together, like let's say you put salt and water. Which one is the solvent and which one's the solute? Which one's the major component when you put salt and water? Water. And so that makes water the solvent. And water is actually a really good solvent in many cases because it's polar. If you have something that is going to be polar, then water is a good solvent for it, or something that's going to be ionic. Saturated is when you can't put any more solute in the solvents and have it dissolve. You guys saw that things dissolved in your lab, but sometimes they didn't dissolve completely. And that made it kind of hard to get that first step right. So Alex said that the actual correct answers on the last lab we did, it wasn't last week, it was the week before, were pretty low. And it, I believe, stems from that did it dissolve or not step. And you saw with one of the tests, when you heat it up, you could dissolve more of one compound, it was that salt. And so how much concentration you can have for it to be saturated depending on temperature as well. So saturated is when you've dissolved everything you can. So if you take a bottle of water, you fill it half full of salt, some of that salt will dissolve, but it won't all dissolve. If you looked at that bottle, you'd say it didn't dissolve probably. But if you drank some of that water, you'd say, ooh, some of it did. And so what you would have there would be a saturated solution where you have as much dissolved as possibly can. And when we have a solution, we like to talk about the concentration of the solution. So the concentration, the bottom part here is the total solution. So the solution means solute plus solvent. Remember, solute is the thing that dissolved, and solvent is the thing it dissolved in. And solution is the total of those two. And solute is just how much stuff dissolved. So concentration is how much dissolved divided by how much total do you have. The units of this, there are different ways of measuring the concentration. So here's one method. Well, actually, this is leading up to one method. One method of measuring it is measuring how many molecules dissolved divided by the total volume of solution. And so if we're going to measure the number of molecules dissolved, it turns out the number of molecules dissolved is probably not going to be 3. It's going to be a really big number. And some very wise scientists, long before I was born, realized that they could make a number that makes it easy to convert units. And that number is called a mole. You guys weren't here when Dr. Friedlein was teaching, but in his general chemistry class, he had a little mole hat, and he would come out and make a big deal about the mole. A mole is this number, 6.02 times 10 to the 23rd, of molecules. That number has a special name, Avogadro's number, and symbol N sub A. So if you have an Avogadro's number, 6.022 times 10 to the 23rd, of molecules, that's 1 mole. And in this room, we have air molecules everywhere. 1 liter of air contains, I didn't look this up beforehand, I believe it's 22.4 moles of gas. And so you could take how many liters do we have in this room, multiplied by 22.4, and that's how many moles, that's how many, 6.02 times 10 to the 23 times 22.4 times the number of liters in this room. It tells us how many total molecules are in this room, which is obviously a very huge number. That's why we use the mole. But there's more to the mole than just a randomly large number. The mole is such that you can take 1 mole of protons has a mass approximately equal to 1 gram. And since a proton and neutron have approximately the same mass, it's going to be the same. 1 mole of neutrons has mass approximately 1 gram. Now I can take this and I can generalize. The actual definition, by the way, is 1 mole of carbon-12 atoms has a mass of exactly 12 grams. That's the definition. But we can take any atom or molecule. For instance, boron. Boron has an atomic mass of, I have to come all the way back here to read it, of 10.8. So if it has an atomic mass of 10.8 atomic mass units, that means it probably has, on average, 5 protons and 6 neutrons for a total of 11 things in the nucleus. If I have 1 mole of boron atoms, that will have a mass of 10.8 grams. That 10.8 tells us the mass of 1 atom in atomic mass units, or the mass of a mole of atoms in grams. So if we look, remember I told you carbon-12 is the definition. 1 mole of carbon-12 is exactly equal to 12 grams in mass. Oxygen, O2. Oxygen has an atomic, has a mass, atomic mass of 16 atomic mass units. So if I have a mole of oxygen, so if I have 6.02 times 10 to the 23rd oxygen, I'm talking about molecules, oxygen molecules, then I will have 16 is 32 grams for a mole of oxygen molecules. And likewise, you can see carbon dioxide, sucrose, sugar, that's a whole lot of carbon, a whole lot of hydrogen, a whole lot of oxygen. It's a very large mass for a mole of sugar. By the way, our next clicker question is going to be doing stuff from this slide, just so you know. So when we talk about concentration, we often will talk about how many molecules, but we won't measure it in molecules, we'll measure it in moles of the solution are in my entire, or of the solute is in my entire solution. And so this example here says, let's suppose that we have 1 mole of sucrose, 342 grams of sucrose, and we put that in 1 liter of water. Then our concentration is the number of moles per total volume. So it'd be 1 mole per liter. Or you could write it as 342 grams per mole if you want it in mass per mole. Or not mass, that's not what I want. That's not what I wanted. Okay, so this is how much is a liter, you might ask? A milliliter is a centimeter cubed. So a centimeter times a centimeter times a centimeter, that's what a milliliter is. So 1,000 centimeters cubed is what gives you a liter. Or it's 1,000th of a meter cubed, if I remember my conversions right. So a liter is based on the standard unit for distance, but it's not exactly that. So our next clicker question, which is open right now, water has a formula mass of 18. How many moles of water are there in 9 grams of water? So I have 9 grams equals how many moles? I know that 9 looks funny. Ivy and Savannah, otherwise known as Danny. All right. So we had 2050. Now I'm going to roll it back to here. And remember, we have the formula mass is 18. We have 1 mole of it. If we have 1 mole, or excuse me, not 1 mole, we have, I've got it here. We have 9 grams of it. If we have 9 grams, how many moles do we have? So basically the question to ask yourself is, what would the mass of 1 mole be? How does that compare to the mass we have? How many moles do we have? So talk to the people next to you on this. Okay, let's go and try answering this again. And after this one, of course, then we will discuss it under my careful teaching. Okay, but what are you thinking, ladies?
We're confused.
Well, that's fine. That's part of learning. You have confusion, you realize you're confused, and then you straighten it out. So go ahead and answer again. The three of you are the ones who have it.
Well,
On your clicker.
oh, on the clicker? Go answer. Oh.
Okay. So after repolling, we had 2, 0, 4, and 1. So very little change. So it's very good that we have this because the correct answer is not the majority answer here. So let's talk about what the mole is again. What is a mole? One mole is the number of protons or neutrons with a mass of 1 gram. And the technical definition is 1 mole of carbon-12 has a mass of 12 grams. So if you take water, how many protons plus neutrons does it have? Has atomic mass of 18, right? That's why it was given. So if I have 1 mole of water, what is its mass going to be? 18 grams. Well, if my mass is only 9 grams, what fraction of 18 is 9? It's a half. So that means I must have how many moles of material if my mass is 9 grams of water? I must have a half a mole. And so the correct answer here was 1/2 mole, because I have half the mass that I would have if I had 1 mole of water. Do you have a question, Ivy? Better to clear up the question than to go home with a question. Okay, Danny has a question.
I do. I don't understand how it's
Okay, so H2O. If you take that, you have 2 times the mass of hydrogen atom. Hydrogen atom has atomic mass of 1. Plus 1 times the mass of oxygen, which is 16. And if I add those up, I get 18. So I have 18 protons plus neutrons. Or in other words, an atomic mass of 18 atomic mass units. Now, remember, there's some approximations here. It's probably not exactly 18, like 18.001 or something. But that is the mass of 1 molecule is 18 atomic mass units. And then by the definition of the mole, that is the number 6.022 times 10 to the 23rd comes from making this definition. The mass of 1 mole equals, and I'm going to take this 18 AMU and multiply it by 1 gram per So this here is a unit conversion factor. The definition of the mole is if I have 1 mole of a material, then an atomic mass unit will have a mass of 1, or if I have 1 mole of material with 1 atomic mass unit, it will have a mass of 1 gram. And so that number in the middle is that conversion factor that is the definition of a mole. And notice you have the grams per AMU per mole, and then I had to multiply by the number of moles to get the total mass. So that means that 1 mole of water would be 18 grams. So since I would have 1 mole would give me 18 grams, and I only have half of that in mass, that means the number of atoms present must be half of a mole as well. Does that make more sense, Savannah? Danny? I'm sorry.
So half of it would be 9. Because you only have 9 grams. So that's
Right. Because I only have 9 grams, that means I only have enough molecules to come to that mass of 9 grams.
only make half of it, which is why
Yeah. Ivy, how about you?
Well, that was the same question.
Are you feeling better now about it? More confident?
Yeah. Could you do one similar to it?
Sure. Let's say that we have, just going back up to here so I don't have to make up numbers. Carbon dioxide has a formula mass of 44 atomic mass units. That means if you add up the number of protons and neutrons in the carbon and the oxygen, you get to 44. And so if I have, and I'm going to choose something that's not a simple number. If I have 10 grams of carbon dioxide, how many moles do I have? Does anybody have an answer yet? Yeah.
0.23.
Is that what you got? Okay, so how'd you come up with your answer, Ivy?
Oh, at first I did it wrong.
That's okay.
So 10 divided by 44.
Because there's 44 grams per mole. Remember with that conversion factor, then that gave us 0.227 with the 27 repeating forever moles. Or as Sam said, just 0.23. Because they only had 2 significant digits, so there's no point in going any further. Oh, shoot. Now I'm out of time. 2 ways of measuring the concentration. The reason we talked about this, the molarity is expressed in moles per liter. Oops, I understand. Moles per liter. So that's part of the reason we had to understand the mole here, because that's a common way of measuring the concentration. So for lab, last time we did it, we had a, 0.5 molar solution. That means that it had 0.5 moles of the solute per liter of solution. Another way that we often do it is parts per million. Parts per million is much more obvious. You have a total number of atoms or molecules and how many molecules per million are this. Right? Wrong. Notice the units here are actually in milligrams per liter. How does that come out to parts per million? I don't know, because milligrams are units of mass, liters units of volume. But that's it. We did a test of changing temperature. You see that sodium nitrate becomes the saturation level, how much you can dissolve, is much greater in hot water than cold water for sodium nitrate. Whereas salt, I said this absolutely backward earlier in today's lecture, salt has the same solubility regardless of temperature. Salt would not have changed at all in our test last week, whereas sodium nitrate would have changed a lot. How do I know that's sodium nitrate? Well, because I did my PhD research on it. I want to get to this last thing. We won't do the clicker question, obviously, but soaps and detergents work by taking advantage of polar and nonpolar molecules. A soap or detergent has one end that is polar and a tail, the entire tail, that's nonpolar. And what happens when you put a soap or detergent in your water is that the water is attracted to the polar end because water molecules are polar. But the other end is pretty much not going to interact with the water. When it comes in contact with the grime, it will have a very weak induced dipole attraction to the grime. And so what happens is you have on your sweater a little piece of dirt. And this detergent comes in, and all of those non-polar tails will attach to that dirt, and the polar heads will attach to water. And then if the water moves, it will move this entire big globule that has the grime in the center and all of these detergent molecules around it out. And so that's how it cleans your clothes. We have to stop here. But so we're not going to talk about purification of sewer today. Sorry. I'm sure that was high on your list of priorities.